Welcome to Chapter 4, where we will be talking about safety. So as you can see, I've decided to change the format of our videos a little bit. Instead of having a video of my face and me kind of talking at you, I decided that we would kind of do a screen capture with a little bit of text and maybe some drawings to go with it. And I really feel like this might be a little bit more engaging and a little bit more entertaining, maybe. to consume this information with. And so today, as we cover safety, we are going to be covering three major areas. Those are going to be biological, mechanical, and chemical areas of safety. And those are typically the three kinds of risk that you're going to encounter in a histology lab. Now, because this is safety, some of the information that we cover is going to be fairly general, because every laboratory and in fact every hospital or research center is probably going to handle safety slightly differently depending on the region and any kind of regulations that come with that. In our laboratory in particular, a lot of our safety things can be found in a big red book, and we intend to have a few of those placed around the hospital. And those big red books tend to have all of our safety regulations that are pertain to some of the bigger topics, and all of our other policies are stored digitally so that we can access them from anywhere. So, of course, the access to the specifics of all of this is going to depend on your laboratory. First, we're going to go over some of the biological exposures. In general, if you think that something is a biological or infectious hazard, most of the regulations go towards just not letting it either touch you or be inhaled by you. Now, that's going to sound a lot like our chemical exposures. The difference is that the purpose is to stop this agent from infecting you. So when we talk about biological agents, we're talking about anything that contains something like HIV or tuberculosis or hepatitis, maybe Creutzfeldt-Jacobs disease, things like that. So a lot of times when we talk about that, we're talking about PPE such as gloves, maybe a respirator. It all depends on what the agent is. Obviously, with any safety thing, having more safety precautions in place is better than not enough, but at the same time, you do have to balance out the effects of those PPE on your ability to move. So perhaps wearing a full hazmat suit in the lab at all times may not be a great idea, just because having too much infringement on your mobility can also be a safety hazard. So it's important to not just take on the full PPE all the time, but you also need to have enough PPE to keep you safe. While we're on the subject of biological and infectious hazards, let's talk about tuberculosis for a second. The current text tells us that tuberculosis is in kind of a state of flux in terms of official regulation on its handling and its exposure. Essentially, the best you can do to eliminate or at least prevent some tuberculosis exposure is the use of a respirator around any specimens that may be positive. Though any precautions that you use will not eliminate that risk completely, and that is something to keep in mind. Associated with TB is the use of cryogenic sprays or freeze sprays. So when you use a freeze spray, typically people use these on unfixed tissue at regular microtomy or on frozen tissue in order to get the block to freeze a little bit more. The use of that spray can actually aerosolize any kind of pathogens that are in the tissue. And so there's been kind of a push by a lot of labs and some regulatory bodies to not necessarily ban the use of freeze spray, but to kind of tell people to use it less and to kind of discourage its use. So that's something to keep in mind when using any kind of freeze spray, is that if it's around fresh tissue or just unfixed tissue, which is typically what we use it on, there's a very big risk of aerosolizing things, specifically tuberculosis. A couple of our biologic risks include things that are bloodborne. So we're thinking about HIV, Hep C, and hepatitis B. So a lot of hospitals will do something like require vaccinations for hepatitis B. Anything that is unfixed fluids, so such as blood, should be handled with care. Oftentimes we refer to universal precautions, and that is an entire training all by itself, which is probably going to be provided by your facility. So I would encourage you to if you haven't had that training yet, get that training. And if you've already had it, please review it. It's incredibly important to practice universal precautions if you're ever going to come in contact with something that is unfixed or just contains anything that might be unfixed. Our last biological hazard that we'll talk about here is Creutzfeldt-Jakob disease, or CJD, or you might hear it referred to as CJ. And the thing with CJ is it is caused by a prion. So typically when we think about something biological, we're thinking about maybe bacteria or maybe something like a virus. CJ is something completely different. It is a prion. And what that essentially is it's a protein. And the problem with proteins is we're so used to being able to find things because they are bacteria, and bacteria have certain properties. Same thing with viruses. You can make vaccines, we can make certain antivirals for viruses because of their structure. When a prion is just a protein that kind of goes around and conforms things in a way that's damaging. Specifically, Creutzfeldt-Jakob disease, the prion gets into your nervous system and just absolutely wreaks havoc. And the thing makes it also so scary for us is the fact that it's incredibly hard to essentially inactivate. It's not technically living. So trying to inactivate this protein is very, very difficult. Also, you might not know if you have it for up to 20 years. The latency period can be 20 years after infection, but once you're diagnosed, then the life expectancy goes down to a few months. So this is something that we really, really need to stress the precautions on. And when these precautions come into place is when you're working on brain tissue. So typically, CAP recommends that all of the any kind of equipment that's going to come in contact with brain tissue that's unfixed needs to be handled separately. The tissue itself has to be in formalin for greater than 48 hours. If it's just a piece of it, if it's a whole brain, it needs to be fixed for 10 to 14 days. And that is just a kind of deactivated some of it. The thing is, even after 10 to 14 days, CJ is not technically inactive yet. So you also need to fix it in something else afterwards, something like formic acid and another round of formalin, or maybe sodium hydroxide at very high concentration. All these things are just to try to inactivate this protein so that whoever's working on it doesn't somehow ingest it. Because once they do, that's it. There's nothing anybody can do for it. There's no vaccines because it's not a virus. You can't take an antibiotic because it's not a bacterium. It is just a protein. And so that's why we have to be extremely careful. And it's also very hard to kill before it even gets inside you. So it's just something we have to be very, very careful about. Our next topic is mechanical safety risks. At microtomy, we have one really big mechanical safety risk. That's the microtome itself. Our microtomes are fitted with razor blades, and we have a chuck that kind of moves up and down against that. And so obviously that creates a very big risk for us. It's something we have to look out for. Now, I don't think I have to tell anyone to not put your fingers anywhere near the blade, especially when it's in operation, but try not to touch the blade with your fingers, ever, if you can help it. Use forceps to get it in and out, if you can. Sometimes if you have a microtome blade box that has a dispenser on it, you can kind of use that as a way of never touching the blade itself. So you can kind of move it from the box into the blade holder and move it the rest of the way in with a pair of forceps. So essentially, yeah, just try to keep your fingers away from the blades, hopefully just never touching them. Also, we have things like broken glass, because sometimes we We might make up a reagent in the laboratory. And sometimes glass breaks. Okay, that happens. Both of these things lead to something that would go into a sharps container. So something to keep in mind if you're maybe starting a new laboratory, having sharps containers is something that you'll use from day one. Within probably the first hour, you might have a bad microtome blade that has to be put somewhere. And if you're in a well-established laboratory, then you have to make sure that you have extra sharps containers, because once they're full, they become a safety hazard themselves. So you don't want people to be jamming things into a full sharps container, because then that becomes kind of its own sharp. So something to keep in mind is that we work with sharps every day, and we have to have a way of properly disposing of those. Now, another mechanical hazard that we'll often run into is electrical. So while we have sharp things everywhere, sometimes those sharp things come in contact with electrical wiring. Now, I don't see a lot of scenarios where a electrical cord might come across your microtome, but who knows? Maybe somebody's moving something around, the blade guard's not up. But also we have a lot of places have office chairs or stools are on wheels, and sometimes the cords get run over. And when that happens, we have to kind of take a look at those electrical components and make sure there aren't any exposed wires. A lot of places have biomed teams that will take a look at these things and make sure that they're still safety compliant. But really, it's also our job to keep an eye on these things. And if we see something that might be potentially dangerous, then we should really report that and kind of take that piece of equipment out of service. Next, let's talk about chemical risks. When it comes to chemical risks, you're going to hear a lot of things about SDSs, or safety data sheets, as well as things like the permissible exposure limits and other kind of labeling systems. So our chemical risks tend to be handled by some sort of outside agency, where they look at the things that we're going to be working with before they even enter our laboratory, before they're even available for purchase. They have to have all kinds of regulations on top of them so that we know exactly what's in them and how they can affect us if we're at varying levels of contact with these chemicals. And part of that is part of the right to know law. And so that's essentially, as workers inside the laboratory, we have the right to know about the chemicals that we work with. And when I say chemicals, I'm talking about things that we purchase and we use in the laboratory. So obviously everything is chemicals, but in a general sense, we're going to talk about chemicals that may harm us in some way. Now, part of having that protection in place involves a lot of documentation, where it has to be assured to an outside agency that our laboratory is providing this information. So we might have to, for example, show that we have our SDS sheets, and somebody might ask a tech, where are your SDS sheets, if you had to look for one, and you have to be able to provide that information and say, hey, it's here. We have it in our hospital information system. Some folks might have it in a folder somewhere. But essentially, you have to be able to show that you have that information available to you, and you can find it any time that you have questions. Something that you're going to hear about a lot on exams and other assessments is the PEL, or permissible exposure limit, of a hazardous chemical. So the one that I always think of, and the one that is often assessed, is formaldehyde. So we'll kind of use that as our example here. So when we're measuring that permissible exposure limit, it kind of comes in two flavors. You have your time-weighted average and your short-term exposure limit. So if either of these things are exceeded during an inspection, or of course any kind of internal testing that you're doing in your laboratory to maintain safety, then some sort of action has to be taken. It might be advanced monitoring, or it could be an actual change in procedure that lowers this exposure. So our time-weighted average is our first one. So that is 0.75 parts per million, and that's over an 8-hour exposure. So during an 8-hour time period, the average exposure for formaldehyde should not be above 0.75 ppm. So your concentration can't get any higher than that on average over 8 hours. Our other one is our short-term exposure limit, which is essentially a short amount of time. So if you have a really big exposure to formaldehyde, that concentration cannot get over an average of 2.0 parts per million over 15 minutes. So essentially what you do for that is you look at whatever area gets the biggest exposure for formaldehyde, and you look at that concentration over 15 minutes. If it goes over 2.0 parts per million, then that you have to take action of some sort. So once again, that can be more monitoring to make sure that that was just a fluke of some sort, or it could be a change in procedure to lower the exposure in the future. Let's say that you're looking over this documentation that's been provided to you, and you might come across a few different terms that seem to kind of point towards the same thing. You might find a toxic dose low, and what that means is that is the lowest concentration known to cause some sort of lethal reaction, and that can be compared to lethal, which is the concentration that tends to lead to some sort of death. And so it tends to be a little bit higher. So on average, it needs to be at least that high to kill whatever has been tested on this, sometimes rats. And you also have something called LD50. And LD50 is the dose at which it is expected to kill about 50%. So that's why you have the 50 there. It's lethal dose 50. Meaning that's going to kill 50% of the tested population, typically some sort of mouse or rat. So at that level, if you tested 10 animals with that substance at that concentration, 5 of them would die. Within the realm of chemical risks, we have things that can catch on fire. So fire and explosive hazards. The things that we really have to concentrate on here, or at least that I would advise you concentrate on, is how to prepare for this kind of event and how to make sure that everyone is safe in case of a fire. And so, because the statistics of this can get pretty deep, you can be looking at things like the atmospheric pressure and humidity of the room, and there's a lot to it. And typically, that kind of responsibility is relegated to somebody with some sort of safety science background. So for techs, for the most part, you want to know where your fire extinguishers are. You might want to take a look at them, make sure that they are A, B, and C at least, just because those cover all different types of fires that you're likely to come in contact with in the laboratory. So let's talk about those for a second. A being something like typically called ordinary combustibles. So think about paper, wood, anything like that. So maybe you have paper or chem wipes next to your water bath. If for some reason your water bath malfunctioned and those things caught fire, then that would be your class A. So that's covered by a class A, B, and C extinguisher. So that's typically all of your normal things you would think would catch on fire. B tends to be stuff like flammable liquids. So think of a grease fire. And where we might encounter that in our laboratory would be paraffin. So for some reason paraffin caught on fire, it tends to turn to a liquid. And so that becomes kind of a flammable liquid with sort of a xylene component, as well as the paraffin itself is a hydrocarbon. And so that tends to take on kind of a greasy consistency when you catch that on fire. But that's also covered by this A, B, C extinguisher. Now the C component covers that water bath, or maybe you have an automatic microtome. You have a lot of different electronic components in the laboratory. If any of those electronic components start to catch fire for some reason, maybe they're shorted out, then you have a class C fire, which is electrical. So this A, B, and C extinguisher covers all of those scenarios. So in most cases, these fire extinguishers that are typically in every laboratory, and they all tend to be an ABC, will cover all of those instances. So if you find yourself in a position where your laboratory specifically advises you to fight the fire, then an ABC extinguisher is probably going to do the trick. But once again, as with any kind of safety thing, always go by your laboratory standards. they're going to cover this day 1. Now, the exception to this ABC extinguisher is a Class D. Now, Class D is flammable metals. So we're talking about things like magnesium or sodium. So if for some reason you're working with metallic sodium in a laboratory, you would know far ahead of time that that was a special scenario, and you would probably have a Class D fire extinguisher ready or something that could take out that fire, because that is now a metal that combusts, typically in the presence of water for sodium. Maybe magnesium, if you have magnesium strings around, if those catch fire, then a Class ABC is not going to do it. You would need a Class D extinguisher for that. So I would say keep in mind that Class D is a thing. If you have any of those things in your laboratory, then absolutely look into seeing if you have a fire extinguisher or some sort of plan for if those things would combust. So let's say you're working with hazardous chemical and some of it spills. Your best bet is to try to contain that spill now. A lot of places will have spill kits available. And what's in a spill kit is typically some sort of containment apparatus. So sometimes it's some sort of pad you might put around the spill to contain it. Sometimes it can be like these long sock-looking things that you put around the perimeter of the spill to keep it from going any further. Now, once you have it contained, what you want to do is deactivate it. A lot of times, places will have some sort of charcoal or some sort of deactivating agent that you can kind of sprinkle on top of it. And at that point, that chemical is not going to react with anything. And after that, it's just kind of cleaning it up however is best. Now that it's deemed inactive, sometimes there might be a dustpan if you can really dry it up with that reagent. Sometimes it just goes into all the pads. At that point, I would consult some sort of in-house safety officer as to how to dispose of those pads and the other things that you have absorbed. While most facilities will typically offer some sort of safety training specifically, we're just going to go over some things that you might run into when you're looking at an SDS, or maybe the reagent bottle itself will be labeled with some safety precautions. So let's look at our HCS sheet over here. And our HCS is just our hazard communication standard. And essentially this is a way of using symbols to tell us other things about the chemical so that there's not as many words. And what that allows us to do is to be a little bit more accessible for some folks. And also it allows us to have a large picture that, let's say a little piece is missing. Maybe a piece of the label's been knocked off. That label should be replaced, but until it is, you can still tell what it is. So if you were to compare that to that, maybe you don't know what the rest of carcinogen is. So you see carcin and you don't know what that means. And so that's what some of these symbols allow us to do. So let's go over health hazard. Health hazard can be a carcinogen, could have some sort of mutagenicity, reproductive toxicity, respiratory sensitizer. It could have a target organ toxicity or an aspiration toxicity. Essentially, these are all things that affect your general health. And so let's talk about flame hazard. Things that are essentially will catch on fire. That's really, there's a means of catching on fire, so flammable means it comes in contact with another flame that catches on fire. Something that is self-heating could be something like sodium hydroxide. You know, when you dilute it, it can be an exothermic reaction. Something can emit a flammable gas. Sometimes if something gives off hydrogen, then hydrogen gas can catch on fire. So next is the exclamation mark. The exclamation mark means there's something acute. Something is going to happen right now when you touch it. And that's to be compared with the health hazard, which tends to be over time. So it has an exclamation mark that means that you're going to see the results of whatever the hazard is pretty quickly, and it's going to affect you specifically if you come in contact with it. So it's something like an irritant, so something that irritates your skin, your eyes. Maybe you get a skin sensitizer, meaning that makes your skin a little bit more sensitive to the reagent itself over time, but in this case it happened pretty quickly. An acute toxicity means that it's toxic at very low levels and tends to show that effect very quickly. Something could have a narcotic effect. I could think something, maybe chloroform might be one of those. So let's move on to a gas cylinder. This one's pretty self-explanatory. You have a gas, it's under pressure, so obviously heating it would be a really bad idea. Dropping it would be bad. So that's more about how to handle the chemical rather than whether or not you should wear PPE with it. Something is corrosive, then typically it's going to wear things down. Sometimes metal, sometimes your skin, maybe your eyes. So it's essentially something that breaks other things down. Something is an exploding bomb, then it's essentially what it sounds like. It's something that can explode. Something like a flame over a circle, then we're talking about things like metallic sodium. So the flame over the circle means that thing that is a solid turns into a flame when it's in contact with something mostly inert like water, in the case of sodium. We're talking about the environment, so this is one of those non-mandatory things, but it's great when they put it on there. Is if it's harmful to the environment, it might have this insignia on the SDS or possibly on the bottle itself, and that means that don't dump this outside. In this case, we have like an aquatic toxicity. Don't put this in regular water. You have to dispose of it at a facility first. And if something has a skull and crossbones, that means don't put this into your body at all, which is a general guideline for anything in the laboratory, but these things specifically will kill you. Aside from that sheet, something that you'll often see on your reagents is this diamond here. So that's your NFPA diamond, and that's kind of a quick way of knowing what you're working with. So the blue one here is your health hazard. So that's the things that kind of happen that affect you personally as a human being. So things like carcinogenicity and things like that are going to be covered in that diamond. And so each side of the diamond goes from 0 to 4. 0 meaning that it's not really affecting you in that way. So if you had a 0 in the health hazard, that means that it is not particularly harmful from a health standpoint. If it's a 4, then it is deadly from a health standpoint. So let's go over to flammability. Kind of the same thing. At 0, it won't burn. If you get to 4, anything, it'll actually have a flash point under 73 degrees Fahrenheit. So it will tend to catch fire at kind of room temperature. We can talk about the instability. So instability kind of says kind of how this thing should be handled and how likely it is to change states, essentially. So if something is very stable, then you should never really knock anything around in the laboratory, but if you drop it, nothing will happen. But if you get up to even around a 3, if you drop it, it may actually heat and detonate. And then the white triangle, or the white diamond, is typically used for something specific. So that could be, don't use water with it if it's metallic sodium. It might be radiation. You might have some sort of oxidizer in there. So the white diamond, we don't see a lot in my laboratory, but other places you might see it a little bit more often. So all of these things are here to kind of simplify that safety experience, meaning that you should have to think as little as possible about this because you're going to have a lot of different chemicals or a lot of different hazards in your laboratory, and these things are here to make that a little bit more simple for you, mostly so that you don't ignore them. Okay, they're trying to keep things relatively easy for us to understand, but also while also conveying the severity of the danger that we're in. And that was it for safety. We did use this new format with the video, so please let me know if this worked better for you, or if you preferred to actually see my lips moving while we were talking about things. Let me know how that went. Next up is going to be laboratory math. I feel like this format's going to work really well for that. You can actually follow along as we go through the problems. And then later on in staining, as we go over the different types, we're actually going to kind of draw them. And we'll get to why that's important later on. But that can kind of offer an opportunity for you folks that are a little bit more interactive, that you can kind of draw along with me if you want. But also, there's the option of just watching and listening, or even just listening to a lot of it. So feel free to let me know what you all think of that, and I'll see you in Chapter 5, Laboratory Math.